Warning, book puns and cool math incoming. Viewer discretion is advised.
Alright, Kai, we've got a big project on our hands and I need your help. Yes, Mr. Boss? A philanthropist and I made a deal. He said that if our printer at our printing company is able to print higher than a rate of 50 books per hour, he will give us, and I'm not kidding you here, $10 billion. Wow, Mr. Boss, that is a novel idea. We are totally bound to do well on this project, and I'm thinking that this will totally be a new chapter for our company. Alright, I need you to investigate if we can reach this rate, and I need it explained to me as soon as possible. Don't worry, boss. I got it covered. After all, we kind of need to be on the same page for this project.
1 day later.
Hey boss, I did some digging and I found our printer algorithm. Here it is. So x represents time in hours since 8 o'clock a.m. and f of x represents number of books produced. So here it is, x squared plus 50 sine squared x. And we're only looking at the interval from 0 to 12. So the derivative of this is... Whoa, slow down. A derivative? What's that? Listen carefully, boss. You know how to find the average rate of change, right? It's also known as a secant line because, according to this graph, it's not the instantaneous rate of change, it's just a line drawn between 2 points. And that's represented by y2 minus y1 over x2 minus x1. I'm sure you know that. You took basic algebra. Even a kindergartner knows that, figuratively speaking. Right. And you would agree that when we want to find the exact instantaneous rate of change at, for example, x1 comma f of x1, which could be any point, as we move x2 closer to x1, our average will become more and more accurate, right? As shown in this picture right here. Yep. Good. So for simplicity's sake, let's call the distance between x2 and x1 h. Algebraically, that's saying that h is x2 minus x1. And let's call the function of x plus h f of x plus h, as shown here. Simple, right? Totally. Lovely. Here's what we have so far. What's happening right here is that x minus x is obviously 0. So here's really what we have so far. F of x plus h minus f of x all over h. But the problem is we can't just stop there. What? Why? It doesn't work because if we just solve this as is and we plug in h equals 0, we'll get 0 over 0. That's indeterminate form. But guess what? I know that you've learned limits in the past, so we can just throw a limit on there, limit as h approaches 0, and here we have the limit definition of a derivative. This is the instantaneous rate of change at any given point on a function. Wow, that is awesome! So we can plug in the algorithm from the machine into the definition, right? Close, Mr. Boss, but there are 3 things that we have to discuss first. First of all, we have to know how to write a derivative of f of x with respect to x. The first of which is dx f of x shown here, but I would stray away from that notation because it looks a lot like the determinant of a matrix. The second one is pretty much one of the most common notations, dy over dx, which represents the differential of y, and y is f of x, over the differential of x. And finally, we have f prime of x, which of course represents this as well. And this notation is probably the best if you're going to stick with f of x and not switch to y. Comprendo. Let's discuss the sum and difference rule now. So for the sum rule, it says that the derivative of the sum of 2 functions is equivalent to the sum of those functions' derivatives, as shown here, where a of x and b of x are 2 separate functions that take x in as their independent variable. Now for the difference rule, it's the exact same thing, but instead of adding, you're subtracting the functions. Sounds logical. And lastly, the last thing we need to talk about before we go into the printing algorithm is that the derivative of 50 sine squared x is 100 sine x cosine x. Usually, I would give you the proof for this, but for the sake of time, I should probably keep this brief, and we can just focus on the x squared part of the algorithm. Cool. Now show me how to find the derivative of the printing algorithm. Luckily, because of the sum rule, we can add the derivatives at the end, and we know the derivative of 50 sine squared x, so we just have to find the derivative of x squared now, because it's added, of course, to 50 sine squared x, to find the derivative of the entire function. Alright, Mr. Boss, let's try and solve this part together. The derivative of x squared is, based on the limit definition, the limit as h approaches 0 of x plus h squared, which is f of x plus h, minus x squared, which is f of x, all over h. So I wrote down some limits as h approaches 0 just for time's sake. And in this problem, as well as any limit definition situation, we have to get rid of that denominator of h. Because if we don't, we will get stuck with a 0 over 0 indeterminate form. Now, we can expand x plus h squared to be x squared, sorry for the handwriting in advance, plus 2xh, that's an x by the way, plus h squared, and of course, minus x squared. Very common mistake, by the way, Mr. Boss. A lot of people, when they do the limit definition, forget to put minus f of x. And of course, this is all over h. Check this out. X squared and negative x squared cancel each other out. That's really helpful. And if you look at what's remaining, 2xh plus h squared, they all have something in common. They have h. And we can factor that out. And we can cancel that out with the h in the denominator. That is a very, very effective idea, a tool we can use in pretty much any polynomial that we deal with in limit definitions. So we have h, and then we have another h right here, multiplied by 2x plus h. We factor this h out so that we can cancel the h's out. Excuse that line, it's really sloppy, but let's continue. So we have limit as h approaches 0 of 2x plus h. And check this out. Now we could just do direct substitution. Yeah! That is like the ultimate goal in any limit problem. As soon as it is perfectly solvable, just directly substitute it. And guess what? The derivative of x squared is 2x. Yeah! Haha, well put, my boy. Why, thank you, Mr. Boss. Now we can look at the printing algorithm. So, the derivative of that printing algorithm is 2x, which is the derivative of x squared, plus, using the sum rule here, 100 sine x cosine x. Ta-da! Now all we have to do is set this function equal to 50 to find exactly at what time this function reaches 50 books per hour. I see. So any value of f prime of x represents books per hour, whereas f of x is just books, right? That's right, Mr. Boss. For the sake of time, let's take a look at it on Desmos.
So if you look on Desmos here, the derivative surpasses y equals 50, so we will get the money.
Yes! Thank you so much, Kai. Man, I knew I should have trusted you. I should probably study derivatives more in depth. Yes, you totally should, Mr. Boss, so then you can move on to the faster rules. There are faster rules? What?